Welcome to the Deep Chat.
Kyle, I have a question for you, a hot take. Is overfitting a problem for large language models that could have big consequences?
Well, this is a complicated question to dive deep in on, but I'll just go ahead and say yes. Overall, yes, it is.
All right, so then let me unpack a couple of the questions about why. The first most obvious one is trademark. Why is that a problem? I mean, why don't you explain what overfitting is and why that's a problem for these large language models?
Overfitting is a problem in all of machine learning, and that's where I consider it and appreciate it the most. Is it's a very fundamental thing that someone who does the low-level actual implementation of training a machine learning model has to be aware of and considerate of. Now, in more traditional approaches, let's say pre-deep learning, when you really did a custom set of features you engineered, and this still goes on today, this is probably the majority of industrial applications. So a classic example is they were trying to build a model that did some sort of medical prediction. It was a radiology task seeing, I think, melanoma or some type of cancer like that from a medical image. And the machine learning algorithm learned very quickly how to tell what were the most severe cases. But when they inspected how is it doing its job, it wasn't that it was recognizing the severe tumor present in the image. It was recognizing that there was one particular clinic for people who were like stage 4, and their images were like a different format than the other clinic that saw a wider range of people, aka more healthy people. So all it did was recognize, oh, this came from the machine where all the sick people go. That's not what we wanted the model to learn, but given the data set, it found a way to cheat and still get the right answer. But it's overfitting because it doesn't generalize. You can't now show it a new image from a camera it hasn't seen and have it do anything useful. It's only able to memorize previous examples it saw.
So how does that tie into something like stable diffusion or these diffusion models that generate images?
So when you have such an enormous amount of parameters in your model, and that's the big difference between the more classical approaches and the contemporary ones, the deep learning approaches, is we're now talking about billions, if not trillions, of free parameters that the algorithm is going to find an ideal setting for. And when you have that many free parameters to be played with, and it's just trying to optimize the math to solve a particular math problem really, really well, it's going to solve some of the problems by just memorizing the data itself. So in the problem, like in a lot of image generation things like stable diffusion, one of the ways in which you might train it is to occlude part of an image and say, ask the model to predict the missing pixels. So based on all of the images you've seen, here we're going to put a black square over something, fill in what you think is probably behind that black censored square. So if all of the training data from that it learns how to exactly fill something in because it remembers the photo it came from rather than like the idea of what might be behind the censored portion, that's a very pronounced way of overfitting. That means that those particular images or ideas or examples are sort of embedded in a way that it's difficult to say where they are, but they're in the model itself.
We both are looking at this Twitter feed of someone named Eric Wallace, and the first picture in there says, the training set had access to an image of Anne Graham Lotz. I don't know who she is. But the caption of that image was living in the light with Anne Graham Lotz. And it's a picture of this woman, very, specific clothing, etc. And then when you prompted this, I believe it was probably stable diffusion. When you prompted it for Anne Graham Lotz, it's practically the same picture. All intents and purposes, the human eye would say, yeah, that's the same picture. Okay, so establishing that, is this the fundamental problem? That if the training set has enough references to Anne Graham Lotz and this picture associated, does it sort of memorize that simply because it's not generalizing to other possibilities? Because there's just not a lot of other possibilities in the training set. It's a very specific name.
Right, but the model is not designed to try and memorize in that way. It's something that happens during the process. So really, if there was a way for a machine learning engineer to turn this off and say never overfit, they would engage that option. In fact, there's a whole set of techniques we call regularization that are aimed at doing just that. But there's no guarantees. It's all a lot of folk wisdom and double checking. This is just a reality of what happens when you have a large model like these. You're going to get some of these cases where the model optimizes by just remembering the exact example rather than some fundamental thing. If maybe there had been more images of this woman, it would have figured out a broader way of representing her in a more compressed fashion inside of itself, but that's not what happened.
Well, it's similar to human memory in the sense that
True.
I could easily, if I was a skilled artist with pencil, I could easily be told, hey, draw a picture of Joe Biden. I might draw a picture that's in my head from some picture I've seen.
Right.
And it looks, like I sat down and copied that photo.
So where's the line?
Does this present a problem for copyright? Now that there's some data out there to suggest that given a training set and the generated image, they can be nearly identical. If I'm not mistaken, the numbers were 1 in 350,000 images, I think it was, that this occurs. Yeah, 100 of 350,000 images were almost copies.
Yeah.
So it's pretty tiny if you think
Correct.
about it.
Yep.
It's a very, very small rate of, if you want to call it an error, small rate of error. We know nothing about law, but I would say it's probably a boondoggle to the prosecution, the ones trying to say that this is a problem. It probably doesn't look good.
You mean it doesn't support their claim?
Well, it probably does support their claim just on the fact that these are almost identical copies. And so the prosecution in this case would be saying these are identical copies and therefore you owe royalties, and you owe royalties to everyone whose images you've used.
Well, no, I mean, you have to show damages. Where was the damages as a result of this process?
I suppose that is correct. It probably helps the prosecution case, though, is my point, that you can even find examples of this and they're pretty well documented at this point.
Well, not if we're saying that this happens in only a minority of cases. If we're saying this is a rare phenomenon.
Well, that's my question. I know neither one of us probably know the answer to that but does the law have room for frequency, right? Because it's such a tiny frequency.
I think it's going to come down to the harm done and who can claim that they have a loss as a result of this. So if that photo, if somebody was trying to sell that exact photo and then they got a very close replica from Stable Diffusion, then I think you'd have a case. But that's not what happened here. This is saying if we do our best, how often can we essentially get the exact input faithfully reproduced out of the other end? It's not the same question as was anyone harmed.
There's a chance, I suppose the way to phrase it is there's a chance of harm in 100 out of 350,000.
Well, it also presumes that the image we get back out, someone does something with it, that they use that exact photo, not some original piece of art that you wouldn't have a problem with.
That's what I mean. There's a chance of harm. Doesn't mean it's going to happen. But I don't know. I'm just wondering if this is, because I could see that if there's a slowdown or if we have to end up figuring out new ways to use a training set, it's going to slow down the development of AI.
Yeah, that's true.
There would be some form of capture of hoarding of data sets that wouldn't be good for the industry, right? If you can't use an online training set, well, now training sets become that much more important.
I'm not sure that that's what would happen. I think there could very well just be an open source movement that pushes these things forward.
Well, that's true, because if you go to Google Images, you can search for free Google images as opposed to ones that have copyright on them.
Yeah, and in ML, there's a long history of people producing these well-curated data sets that everyone's welcome to use, like the Common Crawl is one that was intended to be applied for different web crawling analysis.
Did they remove the problem? I'm not sure if they've done this or if it was a problem, but was it a problem where images looked like they were trying to put in, Shutterfly watermarks?
So that still is likely to happen sometimes. I know I've seen it once or twice. It's not common, but it does occur. And if you worked specifically on that problem of you don't want that to happen, it's something you could probably remove. But otherwise, that's just sort of a natural phenomenon that's been happening.
So one thing that's being said is that future larger diffusion models will memorize more. So that's one of the issues here.
Maybe. Again, remember, people don't want this to happen to their models. It's an inefficiency. It would be better for the model to learn a more compressed representation of the data. That's a better use of the parameters. So they are actively trying to reduce this behavior.
Do you think, or are you hopeful that this will just become a thing of the past, very soon?
No, this is going to be an ongoing discussion. I mean, it's almost to the point where we can anthropomorphize this. Human beings are very similar. When you look at young kids, sometimes they're just memorizing something when you think they're learning the underlying pattern, and it takes a while to get them to see it. ML has the same challenges.
And at some point, we need to be a little bit more flexible in our understanding of machines, I suppose, because at this point, we're used to machines doing what they're supposed to do.
Yeah.
Right. And in terms of, it's binary. It does this thing or it doesn't. That's why I use a computer, because it's predictable, and I can get more work done because I have Google, Excel spreadsheets and things like that. However, in this case, we have to get used to this idea that a computer can provide results that are more closer to what a human might provide.
Absolutely, yeah.
And I think that's going to be an adjustment for people to make. It's going to be an interesting adjustment, but it'll happen over a long time. And that's why when you go back to the last time we talked, I'm saying, and we both agreed, that these things are going to happen slow enough to where we won't even realize it, or we're going to get to the brink of AGI and cross that path. It's not going to be this monumental event that's suddenly going to happen. We'll have moved there in small increments. And I think this step that we're in right now is getting people to accept a new way of dealing with computers. When that shift happens, we'll have taken the next leap into where computers can take us.
Yeah.